Hello again, here we are looking at an A-level maths video. We're in the Pure Maths Year 1 content. We're looking at chapter 3. This is section 3.3 of the book, where we're going to look at simultaneous equations, but this time from a graphical point of view. So here's a quick starter question for you. We've got a straight line graph with the equation which is on the screen there. I put 4 points which may or may not be on that straight line. Your job is to work out which points of those are on the line and which ones are not. Okay, so are you familiar with how the algebra and the graphs kind of match up with each other here? Let's see if we can go through this one. So the equation of the line is given here. All we need to do is just take the x as the x coordinate and the y as the y coordinate and see if it matches up with the equation, see if the equation is true. So for point A, with the x coordinate of 0, we're looking at 2 times 0 here, plus a y coordinate of 6. Does that equal 6? Yes, it does. So that one works. That one is on the line. Yes. Point B, if the x coordinate is 6 and the y coordinate is 0, we'd have 2 times 6 plus 0. And does that equal 6? It does not equal 6. So that one is not on the line. Point C, 2 lots of the -4 plus 2. I think that does not equal 6. If you want to work that out, I've just realized I've made a mistake here. I should have put a 6 there. Forgive me, fix that now. So if this one does not equal 6, then that one is not on the line. And then finally, for point D, 2 times 4 plus a -2 here. That one does equal 6. So that point there is on the line. So to sum up, points A and D are on the line, and points B and C are not on the line. And if we go to the graph plotter here, we can just confirm those are my 4 points here. And then if I put the line on the graph plotter there like that, you'll see, there we go, point A, point D, both on the line, but point B and point C not on the line over there. So how does this relate to simultaneous equations then? Well, for simultaneous equations, what we're looking for really is if we think of these as points on a line or a curve, then each equation will have a whole set of points. And simultaneous equations will be any points which lie on both of those graphs, both of those lines. So when you solve a pair of simultaneous equations, you can relate that in terms of coordinates of points on their associated lines. See if you can have a go at the question on the screen. I want you to solve these using algebra, so no fancy calculator functions for this one, please. Get that practice using the algebra. And then once you've got your solution to the simultaneous equations, write down the coordinates of a point that lies on both of those lines, please. Okay. So there's a couple of different ways you could solve the simultaneous equations here. I'm not going to go through the details here. I will just tell you that you should have ended up with the solution x equals 1 and y equals -3. Those are our solutions, the value of x and the value of y, which solve both of those equations there. So if we think of that graphically, then really the coordinates of the point which lies on both of these lines must be the points with coordinates 1, -3. And we can check that by, again, looking at the graph plotter here. So I've plotted both of the lines here. These are the lines with these equations. And looking at the point of intersection there, there we go, down here at the point with coordinates 1, -3. So this is our result here, really, that we want to focus on. The solutions of a pair of simultaneous equations correspond to the intersection points on the graphs of those equations. So if you want to look at where graphs intersect, essentially what you're doing is you're solving simultaneous equations. Okay, so another question on the screen for you. Please have a go at this one, and you'll notice that this one involves a quadratic here as well. So there may be more than one point of intersection, there may be more than one solution to your simultaneous equations. Have a go at the question, pause the video, restart once you've got your answer. Okay, let's see if you agree with me on this one then. So we will go through this one in a bit more detail than the last one, just to make sure that we know what's going on with these quadratic ones here. So these are our simultaneous equations here. I'm going to call this one number 1 and this one number 2. And if I substitute this y here as x squared into the other equation here, then I end up with x plus x squared equals 6, which is a quadratic equation, right? So I'll just quickly rearrange that. Let's factorize it. So how does that one factorize here? Two numbers which multiply to make -6 and add to make a +1. So I think that's going to be +3 and -2. Okay, and then so that leads us to solutions here. X equals -3 and x equals 2. Substitute these numbers for x back into either of these equations here, but you should end up with x equals -3 and y equals 9, and then the other solution, x equals 2 and y equals 4. Okay, so that's telling us that we must have intersection points at -3, 9 and 2, 4. Okay, let's just check on the graph plotter to see if the graph plotter agrees. So I've got the graphs up here like this, so you can see that parabola for the quadratic shape there and the straight line here. Let's just put in those intersection points, and there we have them there, 2, 4 and -3, 9. The algebra worked out for us. So I'm hoping that you're seeing this connection between the algebra and the graphs here. Let's have a look at the example which I've now put on the screen here, and we're going to have a look at this one together. I'm going to go through this one because we've been asked to use algebra to explain why those graphs there with those equations do not intersect. Okay, now of course we could plot the graphs, we could get some technology, or we could even get some graph paper out and plot it ourselves, but that's not using algebra. So how can we use algebra to explain why these graphs will not intersect? Well, I think what I'm going to try and do is we're going to see if we can just take the two equations and solve them simultaneously and try and find any points of intersection. So let's start off by doing that, because here I can see here y equals 3x minus 3. So if I just substitute that into where I see y in this equation, we're going to end up with 3x minus 3 equals 3x squared plus 7x plus 2. So I've got myself a quadratic equation. I just need to tidy it up a little bit here. Let's subtract the 3x and the -3 from both sides. So if I subtract the 3x from the 7x, I get 4x. And if I subtract the -3 from the 2, or another way of saying that would be adding 3 to both sides, I get this equation here like this. And I need to show that this equation here doesn't have any solutions, because if it had solutions, then it would lead us to an intersection point. Now, do you remember from earlier on in the course, from last chapter, how we can determine easily whether or not a quadratic equation has any roots to it? Okay, do you remember? It's the discriminant, isn't it? So I'm going to use the discriminant to help me with this one here. Discriminant, remember that, b squared minus 4ac. Okay, in this particular case, the discriminant is going to equal b squared, so that's 4 squared, minus 4 times a times c, 4 times 3 times 5. Okay, that becomes 16 minus 60, I believe that number here is. And then that all becomes -44. And the fact that that is less than 0 tells us that we have no real roots to our quadratic equation. Okay, and so therefore our conclusion must be, in terms of the two graphs of these things, there must be no intersection points. Okay, so did you follow the logic of that? Do you understand what we did there and how the discriminant helped us to show something about some graphs there? Okay, and just to confirm, let's have a look at the graph plotter there, and you can see they do indeed not intersect here. The curve, the quadratic curve, and the linear straight line there, they are not touching each other anywhere. Okay, so let's see if we can remember how the discriminant might apply to another situation here. I'm going to ask you please to pause the video shortly and have a look at the question on the screen. Use the discriminant to explain why those two graphs there have exactly one point of intersection. And then, as a bit of a bonus, can you find where that point of intersection is as well, please? Okay, let's see how we got on with this one then. So here are the equations, and I'm going to try and solve them simultaneously. Hopefully you did the same thing here. And when you do that, I think we can substitute the y equals x minus 1 into the second equation here. So 4 lots of x minus 1 equals x squared. Let's just tidy that up a bit here. We'll expand out the brackets, and then we'll put everything all onto the same side of the equation. So we'll have x squared minus 4x plus 4. Okay, so we were asked to use the discriminant, but basically any solution to this equation will lead to intersection points on the graph. Let's look at the discriminants here, the b squared minus 4ac. That's going to be, now the b is negative 4. Negative 4 squared is, of course, 16. 4 times a, which is 1, times c, which is 4. 4 times 4 is 16. So our discriminant equals 0. Remember what that means? It means that the equation here, the quadratic equation we've got here, must have exactly 1. We sometimes use the word repeated root there. So that tells us that we must have 1 point of intersection. Okay. Now, to find that point of intersection, I just need to solve the equation here. So I'm running out of paper space here, but I'll try and squeeze in my solution over here. If I were to solve this equation here, I might want to factorize it, and I'm going to end up with, I think, x minus 2 all squared. So that leads me to just the single root for x, which is 2, and I can substitute that back into either of these equations, but probably the first one is easiest to get y equals 1. So my point of intersection must be 2, 1, like that. Let's just confirm that by looking at the graph plotter here, and you can see that looks like the line here and the curve is just intersecting at a single point here. Let's get the graph plotter to tell us where that is, and there it is, confirming that the correct answer for the point of intersection is the point with coordinates 2, 1. Okay, and that's the end of this video. So this whole section of the textbook really is all about making this connection between equations and the algebra and the graphical representations of those equations. A really, really useful thing for any mathematician to be able to do, to think about things graphically or to think about things with algebra and recognize that there's two different ways of doing that to make connections there. Really good problem solving technique if we can look at things in lots of different ways. But for now, that's the end of this video, and we'll see each other again shortly.